So we are going to do some more problems before we complete this chapter on group actions on a set. So the first problem we are going to attempt today is this. Let G be a X be a G set. Then G acts on X faithfully if and only if no two elements in G have same action on every element of X. So let us start recalling the definition of faithfulness. So X is a G set. Then we define a function from G to Sx. This is the permutations, the group of all permutations on X by phi of G is equal to sigma G, which is defined from X to X. This is a permutation and is defined by sigma G of X equal to Gx. And if the kernel of phi is just the identity permutation, then G acts on X faithfully. So here what we need to do is take two such permutations. Okay, so let G1 and G2 belongs to G, and G1x is equal to G2x for all x in G. That's what it says. These are the permutations. So we need to show that if it is acting on X for all X, then G1 is not different from G2. If we can prove that, then we are done. So G1x equal to G2 of X implies and implied by if and only if G2 inverse G1 of X equal to X for all X in G. And this satisfies only when this is equal to E. So this implies and implied by if and only if G2 inverse of G1 equal to E. And that's possible only if and only if G2 equal to G. So there are not two elements if it is faithful. And that is the End of the proof. Our next problem is, let X be a G set. Then, and let X0 belongs to X and G0 belongs to G. They are fixed. Then the isotropy group of G0, X0, this is an element in X. So this is a isotropy subgroup containing this element, and that is equal to G0, Gx0, G0 inverse. This means actually the meaning of G0, Gx0, G0 inverse means G0 times elements from here. Let us say X prime G0 inverse, where X0 prime belongs to Gx0. That is the meaning of this. And this is a group. This is a group, and every element of group is multiplied or took the binary product of G0 and G inverse on both sides. So these are two subgroups. So we'll try to prove this is a subgroup of this, and this is a subgroup of the other one. So let G belongs to G0, X0. Any element from this. What does this mean? This means that G of G0, X0 is equal to G0, X0. And that implies you take the G0 inverse both sides. So G0 inverse G0 X0 is equal to X0. And that implies, by the definition of Gx0, G0 inverse G0 belongs to Gx0. And that implies you take the G0 on the other side, and the G0 inverse and G0 on the other side. This means G belongs to G0, Gx0, G0 inverse. And that implies G0, X0 is a subgroup of G0, Gx0, G0 inverse. Now let us prove the other way. Let G belongs to G0, Gx0, G0 inverse. And what does this mean? This implies that G0 inverse G0 belongs to Gx0. And that implies G0 inverse G0 of x0 equal to x0. So this implies you take the G0 on the other side, so G is equal to G0 x0 equal to G0 x0, and this implies G belongs to G x0 x0, and that implies G0 G x0 G0 inverse is a subset of G0 x0, implies G x0 G0 equal to G0 G x0 G0 inverse. Our next problem is on conjugate subgroups. So let H and K be conjugate subgroups of G. Then LH and LK are G set isomorphic, where LH and LK are left cosets of H and K in G. So the terms which we need to recall is conjugate subgroups, and we know we have done a couple of problems on G set isomorphisms. H and K are conjugate subgroups of G, implies there exists a G0 in G such that K is equal to G0 H G0 inverse. So, and we know that left cosets of any subgroup forms a G set. So LH and LK are G sets. We already showed that. So we need to define a function from LH to LK such that they are bijective and follows the isomorphism axiom. So define phi from LH to LK by, these are all cosets, and here also it's cosets. So phi of AH is equal to AH G0 inverse, where G0 is the element from G that satisfies the conjugacy. This is well defined because, see, this is actually equal to A. This is first of all, this is an element in LK. That's what we want to show. This is equal to A. Now I'll put G inverse G0. This is actually E and H and G0 inverse. And this is our K. So this is actually equal to A G0 inverse K, and that means this belongs to LK. So this is a function from LH to LK. Phi is well defined because phi of AH is equal to AH of G0 inverse, meaning this phi is independent of A. But if there is an A here, there is an A here. So this is already well defined. So that implies phi is well defined. Now phi is 1, 1 because phi of AH is equal to phi of BH implies AH G0 inverse equal to BH G0 inverse. That implies AH is equal to BH. Phi is onto because this is an element in LH. So A G0 inverse assumes every value, every element in G when A runs through G. When A goes through G, this will become every element of G, and that means for every element of LK there is an element in LH that is mapped using this phi. So this is a bijective map. The only thing which we need to prove is phi of G AH is equal to G of phi AH. That is because phi of G AH is equal to phi of G A H, and that is equal to G A H G0 inverse, and that is equal to G of AH G0 inverse, and that is equal to G of phi of H. And that implies LH and LK are G set isomorphic. Now we'll look into a very useful formula. It's called Burnside Formula. Let G be a finite group and X be a finite G set and R be the number of orbits. Then the sum of all fixed cardinality of fixed groups. These are fixed groups, and you take the cardinality of that and you add it up. That must be equal to the number of orbits times the cardinality of G. So it is a very simple proof. There is not much complication in the proof. So what is xg? X belongs to x such that gx equal to x. Similarly, what is g of x? G belongs to g such that gx equal to x. We are going to use both of this. So for that, we are going to consider this relation. So let gx be all, or let n be the number of all pairs gx such that gx equal to x. So xg, the cardinality of xg from g varies in g, that must be equal to n. Because xg, if you take one g, you get all the x. You get another, you take another g, you get another x, another condition like this. So you add all these sets, the cardinality of these sets, you will get n. Similarly, sigma x of g, x belongs to x, gx cardinality, this is a subgroup of g, that also is equal to n. We will take this one again. We know that the cardinality of gx, this is the number of elements in the orbit containing x, is equal to the index of g over gx. This is the isotropic group, subgroup. And when g is finite, this will become g by the subgroup. And that implies gx is equal to g by the order of, or the number of elements in the orbit. So we will apply here. So sigma n is equal to sigma x belongs to x, gx is equal to sigma x belongs to x by gx. And we can take g outside because this is constant here. So g of sigma x belongs to x 1 by gx. See this one, for each orbit, let us take an example here. D4 set, we have already considered that the orbits in that D4 set are 1, 2, 3, 4, S1, S2, S3, S4, etc. This Gx is an orbit containing x. let's say x is equal to 2. So this is our G2. But when x varies through x, that means you are going through 1, 2, 3, 4. You have all these 1, 2, 3, 4, all these 1, 2, 3, 4, the orbit containing that has got a constant number, and that is this. And that is the, so this will be equal to, see if you run x through 1, 2, 3, 4, what will happen? It will be 1 by 4 times plus 1 by 4 plus 1 by 4 plus 1 by 4 is equal to 1. So this will produce 1 for each orbit, and there are r orbits. So this will become r times, and that is n, and n is this. So that implies sigma G belongs to G, cardinality of the fixed set is equal to r times So let us do one more problem before we complete this chapter using Burnside formula. So it's a computational problem. Compute number of orbits in 1, 2, 3, 4, 5, 6, 7, 8 under the action of the subgroup generated by 1, 3, 5, 6 in S8. S8 is a symmetric group with n elements. So we need to find out the number of orbits. So using Burnside formula, sigma G in G xg is equal to r times sigma. Now what is G here? G here is actually the subgroup generated by this permutation, and that is 1, 3, 5, 6, and that is going to be, of course, you'll have an additive permutation, and you'll have 1, 3, 5, 6, and you'll have 1, 5, 3, 6, and you'll have 1, 6, 3, 5. This is actually 1, 6, 5, 3. So there are 4 elements. So this is actually equal to r times 4. So we need to find out this. So this is actually equal to sigma of G in G xg is equal to x of E plus, there are 4 elements in G, then x of 1, 3, 5, 6 plus x of 1536 plus x of 165. And this is actually how many elements are there. This is what is the definition of this. XE is equal to x belongs to x, EX equal to x, and that is actually equal to x only, the whole of x, because this is identity, and that is 8 plus this is 1356, x belongs to x such that 1356 of x equal to x. None of this will, 1 will be moved to 2, 1 will be moved to 3, 3 will be moved to 6, 5 will be moved to 6, and 6 will be moved to 1. The only elements that are not moved here is 2, 4, 7, 8. So this is actually equal to 2, 4, 7, 8. And that is true for the other two also. So this is going to be 4 plus 4 plus 4. And that is 20. So 20 equal to R times 4. That implies the number of orbits is equal to 20 by 4